Good morning, Vivi. Uh, Today we will discuss about calculus-based optimization. Have you learned about this in uh, calculus or other classes?
Which one, sir?
Calculus-based optimization.
Oh, yeah,
Yeah. Have you learned about Lagrange multiplier?
yeah, we have.
Oh, you have
Yeah,
already.
last semester. Yeah, yeah.
Okay. Okay. So then today is just a review then. Okay. So let's start with that. Right. Can you see it?
Yes.
Okay, great. So, uh, as a background, so if a function is increasing on certain interval, right? So if we have two number, for example, x1 and x2, and in that interval a, b, the function of x1 is actually less than function of x2. You can see the arrow pointing to the right here, right? And of course, we can say that this function is decreasing if the arrow is pointing down. Okay. Now, as a review, okay, a function is called stationary point. Okay, if the first derivative is zero, right? So from the stationary point, you can uh, check whether this is actually a maxima or minima. So there are condition. Okay. So if the first derivative is zero, this is called stationary point. Okay. So this is called the necessary condition for being maxima or minima, but this is not sufficient. So then you need to get the second derivative, right? The second derivative, if the second derivative is positive, then this is local minimum. If the second derivative is negative, then this is local maximum. So this is the review in calculus, right? So let's take example here. So say you want to find the width and the length of a rectangle of area of 100 square meter whose perimeter is as small as possible. So of course, we can do a trial error, but this is inefficient. So better way to use calculus, right? So what we want to know? We want to know the perimeter. So you know the equation of perimeter, right? In rectangle. So what is the equation of perimeter in rectangle? Say suppose you have the width and the height. So what is the equation of perimeter? Say you have a rectangle, okay, and you have the width and the height. Say you have this kind of rectangle, okay, so this is the width and this is the height. So what is the perimeter?
The area. Hmm.
You know,
Is it area?
no, perimeter mean the uh, this area is 8 times w, right?
Mm-hmm.
How about the perimeter? Perimeter is rectangle. Do you remember? So
Oh, mm,
the perimeter is this 8, right? I
mm,
will
yeah.
I color it differently. So So this H plus this A, this W plus this 8 plus this W, right?
Mm-hmm.
So you will have 2 8 plus 2W, correct?
Yeah.
Yeah, okay. So then we want to get, okay, can you find the H and W? Can you find the H and W? If we know the area is 100, so this one is 100, okay? So I want to find the H, okay, find H and W so that the area is 100, but the perimeter is minimum. Can you do it?
Mm-hmm.
So you want to minimize the perimeter
Mm-hmm.
by finding the height and the width, okay? But there is a constraint of area. How do you do that?
Um, so that's oh, we do substitution.
Substitution. How do you do? Can you solve it? You want to share your screen or your
Yeah. Right.
you can share your screen if you want. So
Mm, wait.
mm, how do you solve that?
Mm, let me try it first.
Okay.
Mm, mm.
So
We want to find the H and W, but we want also minimize the perimeter, right?
correct, correct.
Okay. Mm.
So the most important part here is number one, okay, is to formulate the optimization. So can you see it? So the optimization is something like this, okay? So the most important is you should be able to formulate something like this. So minimize, okay, P equal to uh, 2 of W plus H, right? Subject to constraint, what? There are two constraints, right? The first is A, yeah, which is H times W equal 100, right? And then, of course, the width and the height must be positive,
Mhm.
okay? So this is called optimization formula. So in any optimization, what you need to do is doing this first. From the problem, okay, you should be able to create this optimization formula. Easy, right? This one?
Yeah, yeah.
Yeah, yeah. Okay. So then you solve it.
Mm. 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 Yes. Yes. Mm. Mm. Yes. Mm. 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 Mm.
You can create a whiteboard and then you can solve in your whiteboard.
The one for I will share my screen.
Yeah.
Let me try.
Go ahead, please.
Mm. Share screen. So, just like this. So the area, we know it is like
100, right?
100, right?
Right.
And then the area is W multiplied by H.
Yes.
And then the perimeter is W plus 2H.
Yes.
So this we can try to use this next,
Mm-hmm.
and then we can substitute here. So H, and then let's say the here, so H. So we can substitute it here. 100 H.
Mm-hmm.
Then
And
after this, oh, we
okay, 200 divided by 8 divided by
oh
8.
yeah,
Or 8 minus 1. That's fine. 200 by 8 or plus 2 8, right?
yeah, and then
And
we can take wait, we can take the derivative, right?
yes, you can take the first derivative.
Yeah, to make it optimum, right? So with the derivative is
dp d8, right? And then you set to 0, yeah?
that means that this one is dp
Mm-hmm. 8 equal to 0.
and then 8, the 100 is wait, so should be
That one is equal to, yeah,
minus 2, so it's, but let me change it to this.
200 times 8 exponent minus 1. That's easier, right?
Yeah. So
So become
minus
minus 2.
2, so it should be 100.
Yes.
And then
Minus, right?
oh mm, oh yeah, so
Minus still there.
here minus 100.
Minus 200.
And then this one is
Why become 100?
oh yeah. There. So it's 200. And this one is derivative. Derivative should go down to 2.
2. Very good. Then that's equal to 0.
Yeah, that's equal to 0.
Mhm.
That's equal to 0. So
So what is 8?
it's 200 divided by x.
So minus minus no more.
This one.
So 8 square equal.
Square equal to 100.
Correct.
So 8 is 10.
Very good.
Okay.
And then W is?
Instead of 10, so we go back to here, right?
Right.
Here W. So 10, so it's also 10.
Wow, super, Livy. Very good, right? Super.
Yeah.
Okay, so you see here, first you solve for one variable because you have two variables, so you solve for one variable, right?
Mhm.
After that, so you substitute and then you take the first derivative, right?
Yeah.
Okay,
Okay.
excellent. Okay, so that means the square is actually a rectangle with the minimum perimeter, right? Okay, excellent, excellent. Okay, yeah, you solve it. So, okay, now let's practice again. Okay, suppose you have a rectangle. Okay, let me make it smaller. So, suppose you have a rectangle shaped garden. Okay, so he has 50-meter fencing
Mhm.
with which to enclose his garden. Okay, now you want to find the dimension of the largest garden that he can have if he use all the fencing.
Mhm.
Can you solve this? What is
Mhm.
this problem about?
Oh, mm. It's almost the same, right, with the previous
Almost the
one.
same, but it's reverse.
Mm,
So what is
so,
given in this case?
it's close. It's close. So, wait.
What is given? In this case, is given the rectangular shaped garden. So what is 50 meter in this case?
The perimeter.
Correct. The perimeter is to enclose his garden. So 50 meter is the perimeter. And then what you need to know, what to find.
Um, the,
The largest garden, what does that mean?
the area.
The
The
area.
dimension. Yeah,
Correct.
the,
Now my question to you is, can you write the optimization formula?
yeah,
Okay.
it's so the perimeter.
Okay.
So
Can you
it's
write the
same.
optimization
Oh,
formula first?
okay,
Right?
I will share the
Okay.
screen. Okay, share screen.
You can clean this one, or
For
what
this
software are you
one.
using this one?
Oh, this is my phone.
Yeah?
My phone.
Oh yeah, yeah.
Like
What is the app name?
just notes.
Ah, just Node. Okay, okay.
Yeah.
Okay, go.
The first one. Oh, the perimeter. So the perimeter is P, right? So
Okay, so
P, it's the same. So it must be like this, but we already got the perimeter.
right. Uh, can you write the optimization formula first?
Oh, so we want to
You want to
maximize, right?
maximize or minimize in this
So
case?
maximize. It
Okay, you want to
maximize.
maximize. You write maximize.
Oh, yeah.
So you want to maximize what?
Maximize the area. The
Yeah, A equal
equal to
area is just W times H.
W to so
And then subject to constraint.
subject to
Constraint. Okay.
the perimeter, right?
Correct. Perimeter, what is
Oh,
equal? Yeah? P equal W plus H equal 50. Correct. And then what is the other constraint?
it's bigger than
Yeah,
zero.
must be positive, right? So W comma H larger than
Must
0.
be bigger than-
Very good. Very good. Okay, now you can solve it.
Yeah. So first, yeah, we substitute like
Yeah, the same thing, huh?
yeah, but we use the perimeter now. So let's say the value is 50. So let's say we want to substitute 50. And no, it should be the W is that and then
And then to
um
W, so W equal
so we can write it as
25
minus 8.
minus 8. Yeah, very good.
And then we go to the area. The area W is so 28.
Mhm. So now become
The area become 25.8
minus 8 square. Okay, very good. And then
and then we want to maximize so optimum so we can do the derivative.
correct.
The derivative so
dA 8. Okay.
so it should
Oh, that is easy. Yeah.
25
5 minus 2/8. Okay, that equal to 0.
equal to 0 so we can get
So it's equal
25 equal to h. So h is equal to it's about
12.5. Very good. So in that case, now you can get the same, yeah? W.
we can go back to here, right?
Mm-hmm.
Here, so we can get 25. So it's
Mm-hmm.
here is wait, oh,
Mm.
20.
12.5. Okay. So, Levi, can you take the second derivative?
The second derivative of
That one. D28 per
this
dH
one.
square. Yes.
Wait, let me put it here. The second derivative. So it's only minus 2.
Correct. Okay.
Second
So, if the second derivative is negative, what does it mean?
um,
What is the meaning?
forget. Wait.
Okay. Okay, if the second derivative is negative, that means you maximize. Okay, it's a local.
Oh yeah.
Okay, If the second derivative is positive, that means you find the local minima. Okay. Very good. Excellent. Okay.
Okay.
Okay, let's take another practice. Okay. So now we have something like this. Okay. So this is a hobby store with 20 centimeter fencing. Okay. To fence off a rectangular electric train area in one corner of its display room. Two sides up against the wall required no fence. So the question is, what dimension of the rectangle will maximize the area? A little bit different. So you see here, this is the drawing, you can see. Okay, this is a train toy, right? And then it has two sides that require fencing. So the total fencing is 20 centimeter. Okay. The other two sides does not need to have fence because they are the wall. So the question is, what is the dimension that will maximize the area? Again, similar problem. Okay. So first you need to create the
equation.
optimization formula.
Yeah, the optimization formula.
Can you create the optimization?
Okay, so it was 20 centimeters. Okay, I'll go share my screen. Sorry. Yes. So now it's the fencing, it's only half of that. So first we want to
What do we want? Do we want to minimize or to maximize?
the fencing. We want to maximize, right? The area.
Yeah, we want to maximize the area subject to what is the constraint.
Maximum. So maximize A
equal to W times H.
subject to
Subject to, okay. No need to write the constant, is fine. Sub ST is already okay.
subject to constraint.
What
The
is the
constraint is the perimeter.
It's
No.
not the perimeter.
Oh, it's the fencing, right?
Right, it's the fencing.
So the fencing is x plus y.
Is it X plus Y?
Oh, it should 20 minus x. So it's x maximum.
The constraint must be exactly the same like the variable that you put there. W plus H.
Oh yeah, because in the picture.
Yeah.
W plus H equal to
20. Yes. And then, of course, the two of them must be positive, right? Very good. Yes. So this is the first things that you need to do. If you can do this, actually, even if you don't use calculus to solve, okay, of course, this is easy. You can use Solver, Excel Solver, or any other program.
Okay.
To solve, yeah. So the most important part in any optimization in operation research is to create this optimization formula. Okay. Once you can make this, then you can solve using program. Okay.
Okay.
Or you can use calculus. Okay. Okay. Now you can solve using calculus if you want.
So here we can substitute. So we have W is equal to, so we substitute
Minus 8 times 8 second. Okay, very good. Yes. Now just 28 minus 8 square, so that's easy, right? 8. Wow, you're a master of this already. Minus 2h equals 0. So h equal 10, right? So in that case, so w is also equal to 10, right? So now you need to test, okay, the second derivative.
The second derivative is -2.
Okay, minus 2, right?
Yes. Yeah.
Right. So that means you maximize. Correct, right? Very good. Very good. Okay. So now what happen if, okay, what happen if you have unconstrained, okay, something like this. Okay. Now suppose you have several variables, okay, and instead of substitution, you want to do it at once. Okay, so if you have function of several variable like a while ago, right? A while ago, what you did is actually to substitute, right? But actually, you can also do without substitution. Okay, if you want to find the maximum or minimum, how to do that is to find the uh, partial derivative. Okay, so if you want to have a function of x comma y, okay, then you can find the partial derivative. So this is the notation of partial derivative, right? So sometimes we put it into this way. So when we write it fx like this, that means a partial derivative, yeah, to the x. And then again we set it as to 0. Huh? So the solution will be the critical point. Okay? So, and then for the second derivative test, you take the determinant. Okay? Determinant of the second derivative. So this matrix is actually called Hessian matrix. Okay, Hessian. Yeah. So, and then you take the Hessian matrix, the determinant of the Hessian matrix, you will get this value. Okay. So so what is the decision? The decision if the determinant is positive, okay, and okay, the second derivative to x is also positive, then this is minimum. Okay. If the determinant is positive and the second derivative is negative, then this is maximum. Okay. Now, if the determinant is negative, okay, then it has saddle point. Saddle point is not necessarily minimum or maximum, right? Now, if the determinant is 0, then you don't know the decision, right? So this is usually we memorize these problems, okay? Now let's take example, okay? You have this kind of function that you want to find the minimum. So how do you solve this, right?
So
you take the secondary the partial derivative to x, and okay, you take the partial derivative to y. Do you know how to take partial derivative already?
yeah.
Ah, okay, very excellent. Wow. Okay, so okay, when you take the partial derivative, okay, to x, that means the y is assumed to be constant. If you take the partial derivative to y, that means the x is assumed to be constant. Okay, so once you make this, take the partial derivative, okay, and then now you can get this system of equation, then you can solve it using matrix. Okay, so you want to practice this? Okay, try this one.
Okay, now it's my business.
Okay, so I will stop sharing. You try this practice. Okay, so you have you want to minimize this quadratic equation of 3x squared plus y squared minus xy plus 3x plus 5y minus 8.
Plus 2.
Plus 5y minus 8. Okay, now you want to minimize this. Right.
So
So what you will do, right? So first you take the first derivative, partial derivative to x. That means
so it should be only consider the x. So
right,
it should be 6x
6x, and then
x minus y, and then this one 3. Yeah, yes, equal to 0. And then for the y is so and then x and plus 5.
mm-hmm.
0. So
Okay,
we
you
can
can use
say,
substitution or you can use matrix. Do you know how to make matrix from here?
yeah.
Okay,
So
so you separate the coefficient
it is
6 minus 1,
and then
2 and minus 1, okay, and then multiply by
then multiply 8. Multiply by 8.
the factor, right? The factor is what? Okay, multiply by factor x and y, very good. That's equal to
Equal to the result.
the coefficient, okay? But the coefficient, you put it in the right side, so
Oh
that
yeah.
is
So it should be this. Yeah, I forgot.
right, okay.
So after this,
So then that is called matrix A, right? And
oh
then
yeah. So
you have a matrix A
we can
multiply by
first the inverse, right?
correct, right?
We want the x and y.
So
So,
you can
yeah.
write, okay, that's equal to what? To the inverse of that, right? So 6 2 minus 1 minus 1 inverse. Inverse, and then multiply by, okay, the coefficient. Very good. So you remember how to calculate the inverse, right? 2 by 2 matrix.
Yes. Yeah. So this one is 8.
Yes. So 6 minus 1 minus
minus 1 minus,
minus again.
yeah.
Correct. And then
And then
to the
switch this mistaken and then like this.
then multiply by minus 3 minus 5. Okay. What do you get?
is minus 4.
So minus 3 times minus 1 times minus 3, okay,
This-
plus
So 3
1
plus
multiplied by 5 minus 5.
3 plus minus 5. So minus 2. And then 6. 6 plus 36.
6
Yeah, like that. 6.
plus,
Yeah, it should be correct, right?
hmm?
And then
I think there is the sign is,
oh yeah, it should be no. So it's minus, right? Okay, so it should be 24 minus.
it?
Yeah, and it's minus 30 plus 6. Yeah. And then so this is
Wait.
it's
Minus 1 minus 1 multiplied by minus 3 is positive 3, right?
3
And then plus 1 multiplied by
minus
minus
5.
5. So positive 3 minus 5. That means minus 2, correct? And then minus 2 multiplied by minus 3 is positive 6.
6.
And then minus 30.
Yeah.
Right. So minus 24. Yeah, okay. And then what do you get?
So it's half
Half and
6.
6. Is that
We
so?
got the x and
I got different result.
huh? Then
Yeah, I got different result.
wait.
Let me check. So I'm supposed to get 6 minus 1 minus 1 and 2. So an inverse of this one. Sitting for enter. Supposed to be inverse.
Oh, I
The
make a mistake
determinant is
here.
minus
Yeah.
should
This
be
one.
11.
This one it's xi. Yeah, I missed. So it should be
The determinant is 11.
it should be 1 here and then 4. Wait, so 1 minus this and then this one should be 2 and then after that the determinant
2, 1, 1.
yeah, it's the
Determinant is 11. 1 over 11.
yeah. Right? So
That one should be
okay.
2, 1,
Here should be we should flip and then this one is
1, 1, 6. Yeah, correct.
it should be 6
Mm-hmm.
minus 11, right?
Yeah.
Minus 11 it is 3
One is minus 3 and
minus
minus
3.
30. So minus 33. Correct.
So here
Then it must be minus 1 and minus 3.
1 oh yeah
Yes.
minus 1 and minus
1
2.
and minus 2. Okay, excellent,
Yeah.
excellent. Yes, yes. Okay, just computation, no problem.
Yeah.
Anyway, when you solve it, usually you use computer anyway, right? But you're very excellent. Okay, that you can solve this using matrix. I'm quite amazed. Eh? Super. Now try to take the second derivative test. Okay, try to take the second derivative test. That means you will take the determinant of this.
Determinant. Yeah.
Okay,
Wait, I will share my screen. Next screen.
so try to get the Hessian matrix.
So the second derivative is
Okay, make the Hessian matrix first. Okay, yes. So fxx and then fxy
the
and then
determinant.
fyy.
So oh, fxx,
Fxx, fxy,
fxy,
and then
and
fyy.
fyy.
Yes. So fyx is exactly the same as xy, right? So no need to consider that.
Wait, the x is
And
yeah, fxx is 6,
okay.
and then the
Fxy is
minus 1,
okay -1,
minus
and
1,
then fyy.
and fyy 2. Yeah.
Okay, 2. And then now you create the matrix, the Hessian matrix. So H equal, so you form the matrix, and then you can calculate the
Oh,
determinant.
wait. I guess there is a function there. Oh, like the determinant is like fxx, fyy,
Xy, no, no.
minus f.
Oh, okay, if you want to calculate directly.
Yeah. 6 is 2. This one is 1.
Y squared.
So the determinant is yeah.
Determinant is positive.
Oh. Oh yeah, it should be.
Yeah. So determinant is minus minus.
Oh no. Oh no, it's minus or plus, yeah.
Yeah, it's positive, right? So that means you minimize, right? Okay. So you minimize that.
Okay.
Okay. Very good. So okay. Now there is another method for constraint. A while ago, what we discussed is unconstrained, right? So there is another method called constraint Lagrange multiplier. This is to solve constraint optimization. Okay, so the technique is rather simple. So you have the function, the objective function, which is fx, okay, subject to constraint of g equals 0, right? Then what you need to do is to form what is called Lagrangian. Okay. Then you have introduced one variable called lambda. So this lambda is called Lagrange multiplier, right? And then you form Lagrangian function. So this one. So earlier you have f of x comma y. So now you create a Lagrangian function with this function of x, y, and lambda, right? So the way you form is like this. So fx comma y, this is the objective function, minus, okay, the Lagrange multiplier multiplied by the constraint function, which is gx comma y. Okay, and then to solve this, okay, you take the partial derivative to x, you take the partial derivative to y, and then you take the partial derivative to lambda, and all of this equal to 0, then you can solve the Lagrange multiplier problem. Okay, so the problem with Lagrange multiplier is we don't know the second derivative test. Yeah, we cannot know whether this is maximum or minimum. But this is quite important technique. Okay. So try this. Okay, can you try say you want to minimize the value of this one, fxy equal to x multiplied by y subject to constraint of this one. So then what you need to do is to, from the Lagrangian function, okay, so fxy is xy minus the lambda multiplied by this constraint. So look at the constraint here, okay, you need to put the constraint such that the right hand side is 0. So in that case you minus, okay, so 2x plus y minus 3, right? Because our goal is to create so that the gx comma y in this case must be gx comma y is equal to 0. Okay. Okay. Let's can you try this? Suppose you have this problem. Can you solve it?
Okay, 2x plus 2. Okay.
Mm-hmm.
Plus 3.
You can share your screen.
Okay. Yeah. So firstly,
Yes, the most important is to create that optimization formula, right?
one, two, calculate that. So we use this
2x plus 3 equal. Yeah, okay, very good. You want to
constant is
minimize.
lambda. The constant is lambda.
Oh no, you now you create what is called Lagrangian function. So let's call this capital
Yeah.
F.
So
So you create F, capital F. Okay, that is a function of x, y, and lambda.
this is y,
Function of x, y.
y lambda.
It's okay. It's okay. X, y, and lambda. Okay, which is equal to the objective function
The objective function is
x multiplied by y, xy, right?
y
Okay, minus
minus the constraint.
lambda multiplied by the constraint. But the constraint must be gxy equals 0. That means you put the right hand side to the left hand side.
Okay, so
2x plus y minus 3. Very good. Okay, now you already formed the Lagrangian. Now what you need to do is to take the partial derivative to x, partial derivative to y, and partial derivative to lambda, and then all of this equal to 0. So del f,
Oh, yeah, del.
correct, correct. Yeah.
del
F.
del F1 del F
Uh, if you already put like that, you don't need to put del. If you put del, must be divided
del
by.
X, but
Yeah.
okay. Del X1 lambda. So
What I mean, Livy, if you want to put the notation, yeah, you either put del F del X,
oh, del X.
yes,
Del
X,
X. Yeah.
or you put Fx. That is the same.
Just put Fx.
Okay.
Okay.
Yeah, you put Fx is okay. Fy, F lambda. That is fine already.
So here the X is 1.
Okay. How do you solve this?
This
Okay.
one is
Minus
2 lambda equal to 0. And then this one is 2 to y. Y is 1. So lambda equal to 0. And then the last one is the lambda. The
yes.
lambda
So
is all
the
of
objective function is no more. Minus 3.
Oh, this one is minus, right? Yeah, minus. So should,
Yes. Minus.
yeah. And then
And then
we solve we do sub. No, we substituted. No.
yeah, and then you can just solve it. After that, it's just algebra. That one, F lambda is also equal to 0.
Oh, this one.
No,
Oh, no, this
yeah,
one. Yeah.
okay.
Right.
Right.
Yeah. Okay.
Yes, and then now you can solve for x, y, and lambda.
Wait, we got it here. X equal to lambda, and then
Lambda, in that case,
equal to
y equal
lambda.
to lambda.
And then for this one, we can substitute.
Right.
Okay, so
Substitute. So minus 2x.
minus 2 lambda, and then minus
2 lambda again.
and then plus 6 equal to or wait, I just
Why minus plus 6?
no, it should be
Plus 3, right?
minus.
And then minus. Why become minus 6?
Because I move it to the right hand side. Here it's the equal, right?
I mean, from where do you get 6?
Oh, no. Yeah. It's 3.
Okay.
Yeah, it's 3, right? Yeah.
Okay.
So,
And minus 2, that minus 4.
minus 4 lambda. So should be 2 equal 4. Correct, right?
Yeah. So my slide is wrong, okay? So because I put 2 there. You're correct in this case. Okay, now you get lambda. Now you can get that. So x is equal to lambda, and then y is just 2 times that. Right.
So the
Y equal to 6
so
over 4. That is
3.
very good. Excellent.
Okay.
Okay. So the one in my slide is wrong, sir. You corrected already. Excellent. So you know how to solve using. Okay, now let's solve the earlier problem that you have. But this time you use Lagrange multiplier. Can you?
Which one?
The electric train.
The electric.
This one.
This
Can
one, right?
Uh, this
One.
Yes, this one.
Okay.
Okay.
Oh,
Okay. Exactly the same, but this time you use Lagrange multiplier.
multiplier. Okay.
Okay. Okay, you can share. So you want to practice? Oh, Joy is
I
already here.
haven't seen the previous problem.
Okay. You can follow from the slide in Lentera.
Yeah.
Okay.
So,
So you can follow from there. Yeah, I give very simple examples in this slide. Of course, this is just a review. I think you learned this already in other classes, right? In calculus also. Right. So it's just today is just review. Yeah. Looking at your capability, I'm amazed. So this is very excellent. So
Do
the
you want
most
me to share?
you can share screen if you want, yeah.
I don't have like a writing pad, so I'll just zoom my paper.
Uh-huh. Or you can use the what is that? Whiteboard.
Using trackpad, sir, so it will be very messy.
Okay,
Or I
okay,
can type.
go.
Wait, give me a moment. Can you see? Wait, it's very
Can you
hard.
share it?
Cannot share. Wait, I just try to use whiteboard. I'll type. So the problem is f x
First, you
y.
create you try to create the optimization formula. That is, what do you want to maximize or minimize?
Maximum area equals to x multiplied by y.
Okay,
Subtract 2 x
so you
plus
want to
y.
maximize, right? You write maximize. Okay, very good. Subject to, and then x comma y larger than 0. Very good. Yeah,
Mm,
larger than 0. Excellent. Then now you create Lagrangian, yeah, lambda L.
just use L.
You can use any. Yeah. Minus L times gx, comma y.
So it will be.
That one is xy minus L multiplied by x plus y. Excellent. Okay, excellent. Okay, maybe we can write different functions so that we will know this is different. So can you make it capital F for this Lagrangian?
Okay.
Xy. So
Later.
what I mean is, can you probably write this one as capital F?
This one.
Yes. Yeah, because that Lagrangian, right? So that we
You
will
want
know.
me to write?
No, because you have this is a little bit confusing because now you have F and you have another F here, right?
Oh,
So let's make this capital
okay.
F.
So I'll
Okay.
just.
Yeah, yeah. Just to make it different. Okay, excellent. Yes. And then this is y, and how you will take the partial derivative. L multiplied by fx minus, okay, equals 0 also. And then, yeah, this is the easiest, yeah. So you just exactly the constraint, yeah? Minus 20, okay, equals 0. Yeah. The rest is algebra, okay. After that is just algebra. So you know that x equal lambda, y equal lambda, equal x, right? And then put everything in lambda. So minus lambda minus lambda plus lambda. That means minus 2 lambda minus 20. That means lambda equal
Minus lambda plus lambda equals to.
minus lambda plus lambda equal the FL, the FL. You just put back into the third equation, right? So Joy, I think this one is negative.
Which one?
You put this value into this one, right?
Cannot see your annotation. Oh, okay. Oh no.
Oh no, oh no. Oh
Okay,
my
okay. It's
goodness.
like,
Sorry, sorry. Okay.
wait, I need
So
to.
that you can undo. Only by throwing. So
Yeah, minus lambda. Oh, wait. I forgot to multiply the.
right. So this one no need lambda in the left hand side. So yes, 2 minus lambda minus 20 equal to 20. Right. So then L equal to minus 10. Very good. Then, of course, now you can get x and y. Right.
It should be positive, right? The L.
Should be positive. Yeah.
Yeah. You
Why this
the
negative?
you haven't multiplied the, yeah, that one should be the positive
Oh,
one.
the 20. Yeah.
Hmm.
Yeah, the 20.
Ah, yeah, the 20 must be positive.
And it's like this.
Correct. Yeah. Okay. Very good. Okay. Excellent. Super, super. Right. So, can you distinct earlier? Okay, we practice using calculus, right? The same problem, and then next is using Lagrange multiplier, right? So in calculus you use substitution so that you can make it into one variable, right? And then using Lagrange multiplier you use partial derivative, right? So that's the difference. So I have an assignment here. Do you want to do it now or you want to do it as assignment? In the
You can do it now.
Yeah.
okay, you can do it now if you want. Right. So here you want to minimize the construction costs, right? The company is planning to construct the warehouse, okay? Or you can do it in as assignment, that's also fine. Okay, so a little bit more complicated. So can you use Lagrange multiplier in here? Okay. So this is the clue, huh? That the total cost of the building is now three variables instead of two variables. Now you have three variables. Right. So you want to minimize the construction cost. Okay. And what do we have? The volume is given, right? The volume is given, and then each part of the construction, wall, floor, and ceiling is also given. So what will be the cost function? And then you first you create the optimization formula, huh? Okay. And then you find the minimum. Okay. Uh, Here it is. Before we go, I want to share with you something else. Okay, I shared there in Lentera my note, right? So this is exactly the same as earlier. This is my note. I already put in the slide this one, this example. So this is also exactly in the example. I think I make mistake in here. Must be 3. Okay, anyway, so the one that I did not put in the slide is this part. Yeah, this is a little bit more advanced, but at least you will know how to deal with more complex form of Lagrange multiplier. Okay, so this notation is called the first derivative. So this is called gradient. Can you see it? Right. So this is called gradient. So and then say if, for example, if you have two variables, so you take the first partial derivative to x1 and x2. Right? If you have many variables, then you can just take to become a factor of partial derivative to x1, x2 until xn. And then you can also form the Hessian matrix like a while ago. Okay. And then if you use Lagrange multiplier, so now you can have many G. Okay. So this G, the constraint is now G1, G2, so GK. Okay. And then now what happened is this. Okay. If you use Lagrange multiplier, the GK must be equal to 0, right? Right? So what happened if your GK is not equal to 0? So yeah, I said here the Lagrange multiplier is good for equality constraint. How if you have inequality constraint? So if you have inequality constraint, right? All inequality must be all inequality can be multiplied by -1 to reverse the sign. Okay, so then you need to have what is called Karush-Kuhn-Tucker condition, KKT condition. Okay, so if, for example, if you want to find this problem subject to constraint of G equals 0 and H is less than 0, okay, then you need to find that by putting this formula here. Okay, so the G you see here, this part, so this part is what? This is the objective function part, right? And the second part here is the constraint of equal 0. Okay, and then if you have something that not equal to 0, that is minimized, then again you put here. Okay, then you need to have additional constraint for that. So this is the additional constraint that you need to put there. Anyway, so at least you know, okay, at this point, okay, at least you know that you can also use Lagrange multiplier for something that is inequality constraint. Okay. Okay, so now if you want to practice your assignment, you can do. Yeah, if you finish, then no assignment. If you did not finish, then become assignment. And then when you finish, you can share your solution. Okay, I'll pause the recording.
Do you want us to use Lagrangian or?
Yeah, can you use Lagrangian function?
Wait.
The most important part there is to create the optimization formula. Okay, because once you create the optimization formula, either you can do it manually, like today, what you do is using Lagrangian, or you can use computer to solve it, right? So from the problem at hand, okay, you need to know how to create the optimization formula. That is maximize or to minimize something, okay, objective function subject to constraint or other constraint. So when you can create the objective function and the constraint, then actually you are done, okay, with your optimization problem, because all you need to do is now you put that into computer and then you can solve it. So you have 4 wall, 1 ceiling, 1 floor, right? Can anyone share the cost function?
I can share.
Hmm.
Okay, I will share. Here.
Okay, okay, that's the volume. Okay, and then you want to minimize the cost.
Mhm.
Cost is the floor.
It's
The
your-
floor is W times L times 4. What is this for? 4 is the cost. The cost,
that.
right?
Mhm.
The floor is 4, correct. And then the ceiling. The ceiling is again. Oh, why you multiply by 4
Ah, yeah,
in the
yeah.
beginning?
It should be like this. Yeah, no. So wait, I forgot that nah.
Yes, okay.
So wait. So I forgot. Yeah.
And then the wall. The wall is h times w. Okay, that is 2 times, and then x l times the h, that is 2 times also, that is correct.
Mhm.
And then what is this? Multiplied by 4 multiplied by 3. With the wall, the cost of the wall is 3, so
Oh
multiply
no,
by 3 only.
I forgot that I have already put the
Multiply by 3.
3. Yeah, so it should
So the
be
ceiling cost is also 3, that's correct. Okay, excellent. Okay,
this. Yeah,
yeah.
so right. Yeah.
So you get 4, 3, 6, and 6. Okay.
This one is the same. I combine it.
Right. So then you put them together. Yeah. WL 7 and then W8 and then L8. Very good. Subject to constraint. What are the constraints?
The constant is the volume, right?
Correct.
So I
Something
write
that you know become the constraint, right? So WLH equal to 252,000. Okay.
Yeah.
And then what are the next constraint?
Then, oh, everything was
Positive.
positive.
W comma L comma H must be positive. Okay.
Okay, so
Excellent. Okay. So once you make this, you can actually put that into computer. But now let's solve this using Lagrange multiplier.
So
So
of
L
L and H and also
and lambda. Excellent. Okay, equal to that.
So
Objective function.
the objective function is
That one, the
this
fx.
one. So it's
Actually, that is not fx. Nah. So that is should be f of w, l, and h. Right?
Okay.
Yeah, because there is no x there.
Right. Okay. So this should be the objective function.
Yeah, that is
So
7wl plus 6w8 plus
6L
6l8
right? Minus
minus lambda multiplied by, you can put down
the constant is so
WL8 minus 252,000. Okay, very excellent. And then now you take partial derivative to W, to L, to H, and to lambda. Yes. Okay.
So W is 7L
7L
6
6H, and then that one
W.
is WL8.
So minus lambda LH. And then for the L is
L
7W
W
plus
6H,
6H
okay, minus lambda times
H.
W.
The H is 6W plus 6L and then WL.
So WL. Okay. And then the
So
lambda is minus
minus
everything there.
W.
Okay, it's minus again. Okay. Then everything is equal to 0.
Equal to 0.
Yes. And then you can solve it, right?
Yeah.
Yeah. Okay, the rest is just algebra. Okay.
Yeah.
Very good. Okay. Excellent, excellent. So you have no problem, right? Also, right? I think you get the same.
Oh yeah,
Yeah.
I'm finishing with the algebra.
Yeah. Okay. You want to share?
Wait, it's on paper, sir. Wait, give me a moment.
Okay. Okay.
6.
I use an online calculator to solve the algebra. It's too
Oh,
long. But then the answer is 70. The total minimum cost is $75,600,
mm-hmm.
with the points being x60, y60, and z70.
And what are the
Is it
dimension?
correct? The
What
dimension for it's 60,
60 and then
y is 60, and z is 70. The height is 70 centimeters.
Livy, did you get the same thing?
But I'm still to the
You think?
calculation.
Okay.
Yeah.
Okay, so after this we will take a break, right? Once we come back, what time you should come back? 1 o'clock?
Yeah.
We will have
Yeah.
we will discuss about introduction to optimization. And I put link there in Lantera about minisync. Did you see that? You can also download and install that program if you want to. It's a free software for optimization. Anyway. One nice thing about minisync is it also can do constraint satisfaction problem, yeah, CSP. were you able to download the Minisync?
Yeah, I'm able to.
So this is an optional for if you want programming in Minisync, that is also okay. But mostly we can use Excel actually. But there are certain things that we cannot do in Excel, which is the CSP, constraint satisfaction problem. So now in Excel, we can only do maximize or minimize, right? But we cannot do what is called satisfy. So the reasons of optimization problem will include not just maximizing and minimizing, but it also include satisfy. Wait, I have a tutorial on that. Satisfy. Oh, I put that in tutorial of Cripps arithmetic. Okay, I will put in the chat. You can see this tutorial of Cripps arithmetic. This is the example of constraint satisfaction problem, or constraint programming. For example, send plus more equal money. So, yeah, send plus more equal money. And then we need to find out what is S, what is E, what is N, what is D, what is M, and so on. So, okay. So of course, we know that because in the usual way we compute, so S in this case is multiplied by 1000, right? E is multiplied by 100, and then N is multiplied by 10, and then D is just multiplied by 1. The same thing with more. In that case, M is multiplied by 1000, O is multiplied by 100, okay. R is multiplied by 10, and then E is multiplied by 1. Okay. That equal, right? So expression 3 in this case is money, okay, is equal to M in this case, because this is how many? 1, 2, 3, 4, 5, right? That M in the first year multiplied by 10,000. O is multiplied by 1,000. Then N is multiplied by 100. And then E is multiplied by 10. And then Y multiplied by 1. Right? So when we said send plus more equal money, that means expression 1 plus expression 2 equal to expression 3. And then we want to find out the value of S, E, N, D, M, O, R, and Y. So this is a permutation problem and not necessarily all different. So in this case, we cannot use Excel. So I'm using MATLAB in this case, but there are so many solutions. Okay, and this is the actual solution. So this kind of problem you can use Minisync to solve it. Okay. So this is a new direction of research, I don't know, in optimization. One is usually what we are dealing is either maximizing or minimizing, right? But the third one that is recently is about calling not just maximizing or minimizing, but satisfying. Okay, so let's take a break and we'll come back at 1 p.m. Is it okay?
Okay, sir.
Okay, thank you, sir. See you.
We'll see you later. Let's start again. Thank you. Okay, so we will discuss the next topic, which is introduction to optimization. So you can follow the slide from Lentera. Okay. Okay. So again, this is still review. I think you have learned this, I hope, last semester, right? So, okay, so this is the topic that we discussed, so including the CSP. So we have unconstrained constant optimization and what is called standard optimization model. Okay, and then we can transform the objective and constraint, and what if the constraint is inequality, and some classification of the optimization software model, and then the software. Okay. So question is first, why do we need to optimize, right? So one reason is to reduce the waste and cost, right? That can lead to higher profit and success. Okay. So nowadays business are very highly competitive. So we need to improve the efficiency, okay, increase productivity, and enhance performance. So these are the reasons to optimize. By optimizing, we can reach not just a small percentage of the profit, but it can double, triple, even sometimes 10 times, yeah, based on how much you optimize. Okay, so by learning optimization, which is in operation research, the most important part here is not to solve the problem, okay, because you can do problem solving using computer software, right? So the most important is actually in learning OR, yeah, is your ability to transform the real world problem, so okay, usually in the word problem, right, into the optimization formulation. Okay. After that, you can just input this optimization formulation into Excel solver or any optimization software. Okay, so for example, R, Python, Minisync, Lingo, and so on. So now in learning any OR algorithm, the most important aspect is to know the assumption behind. Okay? What is the invariance? I think last week we discussed about invariance, right? And then what is the strength and weakness of each algorithm, and you just get the general idea, okay, on how it is done. So why the algorithm work and why is it created and so on. Right. Okay. So this morning we discussed about unconstrained and constrained optimization, right? Unconstrained means you only have the objective function, either maximize or minimize the objective function without constraint. Yeah? So now this is example, okay, of optimization without constraint. For example, you have minimize x comma y of some quadratic function here. Okay? Then you will find the solution at x equal y equal 1, okay, which will give you the objective function of f min equals 0. Now, I think you don't need to practice this, right? But I think it's very easy for you to solve this, right? So, say you want to maximize this function, okay? Then you take the first derivative, equate it to 0, and you get the x, and then you put into the function itself to get the value. To check whether this is maximized, then you take the second derivative, right? Okay, and then the second derivative must be positive or negative in this case. If you want to maximize, the second derivative is positive or negative?
Negative.
Yeah, negative, yeah. Okay, so now this is what is called general optimization problem. So in general optimization problem, you will find the x, okay? X is a factor here, okay? Either to maximize or to minimize the objective function subject to constraint three things. Yeah? One is equality, so say hj of x equals 0. Second is inequality, so can be less than 0 or larger than 0 or certain value. Anyway. And then there is some boundary condition for each x. You will have lower or larger value. Okay? So these are the very general optimization formula that you supposed to make in any problem that we will face. Okay. Now, aside from this general, we have also what is called standard. Why this is standard? Instead of maximizing or minimizing, we just maximize. So we standardize by saying, look, I just want to maximize the objective function. Second, that make it standard, it has only less than inequality constraint or an equality constraint and the boundary condition, of course, right? So there is no larger than inequality constraint. So then you will ask, but what if your problem actually minimizing? What if your problem actually has some constraint that is actually larger than 0? What you will do about it? Any idea? Joy, what did you learn last semester? Suppose I want to minimize, but your standard optimization problem is actually only maximize. So suppose you have a solver that can only maximize. What are you going to do? Livy. You learned linear programming, right, last semester? Right. What happens if you have objective function that you want to maximize? Okay, if your solver can only maximizing, but your objective is actually to minimize.
Multiply by -1.
Correct.
Yeah.
Correct, right? So the objective function you multiply by -1, okay? Then the maximize will become minimizing. Okay. How about the constraint? What if your standard constraint is actually only less than equal or equal, but you have constraint that is larger than 0? Do you remember?
If the constraint is larger than 0,
Then what you should do? You remember?
can we use the big M? No.
What's that?
We use the big
Big M.
as a very large number of constant.
I think you can add another constraint. Not
You add another constraint. Okay, so okay, here it is. Okay, so any inequality, okay, that is actually larger than 0, okay, if you multiply by -1, it will become less than 0, the same. Okay, so if your constraint, for example, larger than 0, gi x here is larger than 0, so you multiply this constraint with -1, then that is equivalent to gi less than 0. Yeah, so the same as your maximizing, if you multiply by -1 become minimizing, but in the constraint, okay, so if your constraint is actually larger than 0, you just multiply by -1. Okay, so there's another way. There is another way. Of course, you can use big M and so on, but there's another way is to use these two dummy variables. What is this for? Slack variable, surplus variable. Do you remember? What is that? What is the purpose? What is the purpose of having slack variable or surplus variable? I think you have learned this last semester, right? Suppose? No? Yes, okay. So what is the purpose of slack variable? What is the purpose of surplus variable? What is that?
to become equal.
Yes. Okay. So if your constraint is unequal, so either larger than or smaller than, okay, you can transform this into equal. Okay, so inequalities can be transformed into equalities. Why you want to transform into equalities? So that you can use linear algebra, right? So without transforming this, then you cannot solve using linear algebra, right? Because you still have larger than or smaller than sign. Okay, so to make this, so if your inequality constraint is actually g, okay, is less than, okay, then bk, then you create what is called slack variable. This slack variable xk must be positive, yeah? So or 0, yeah? Positive or 0, so non-negative. So gk plus xk equal to bk. So now from unequal, right? From inequality like this, now you transform it into equality by adding slack variable. So slack variable is basically dummy, yeah, that you can add so that it will become equal, right? The same thing, if you have inequality constraint of gk is larger than certain value, bk can be 0, right? Then you add or you subtract with non-negative surplus variable, so that it will become equality. Okay, once you make it equality, then you can just use a times x equal b, isn't it? The constraints become like this. So is it clear? Right? So let's take example, okay? So suppose you have 5x1 plus 6x2 less than 20. Yeah? Less than 20, so what you will add? You will add slack variable, right? So that you will make it equal. So in that case, you can add new variable, so x3 or s1, okay? Okay. So that this s1 is basically the slack variable. Okay. So what is the value of s1? Is equal to 20 minus 5x1 minus 6x2. Huh? Okay. So of course the s1 itself must be positive, yeah, or 0. Up to here, is there any question? Clear, right? Yeah, you already learned this last semester. Okay. Now, here is called linear programming, yeah, and we call this standard form. Why? Again, when we set standard form, that means you have to maximize the objective function, okay, and then there is only equality constraint, yeah, there is no inequality, okay, except for the boundary condition, right? So this is called the standard LP or linear programming problem. Yeah? So again, if you have problem that is actually minimizing, so you multiply by -1, okay, how to make it equal from unequal, then you add either surplus or slack variable. Okay. Now, optimization problem can be classified something like this, right? So when you have a problem, okay, think about it. It's how many objective function? Okay. Usually you have only single objective, or you can have multiple objective. Yeah? So, and then check the problem is constrained or unconstrained. Eh? And then check also what is the variables. Okay, the variables are continuous, yeah, discrete, or mixed between continuous or real number, yeah, or discrete, yeah, mixed between discrete and continuous. And then in terms of the function itself, it can be linear or non-linear, okay. And then you need to check whether the actual problem, okay, the constraint and the optimization is convex or non-convex, okay, whether the problem is differentiable or non-differentiable. Okay. So based on this classification, then you start to think about what kind of algorithm you will use. Okay. For example, if the problem is linear, convex, right, continuous, either constant or unconstrained, you can use linear programming. Right? But if your problem is integer or mixed integer, okay, and they are non-linear, so probably you cannot use linear programming, but you can use other algorithm. Okay? And if your problem is actually non-convex, then you cannot use the convex algorithm, then you can use other algorithm that actually for non-convex. Okay. What do you mean by convex? Convex is something like this, okay? So if you have x and y, okay, and you have a parameter t between 0 to 1, okay, a space is called convex if you can have satisfy this function. What is this function about? Okay. This function can be put into one dimension, something like this. So convex curve is this kind of curve. Okay. When you put a linear value, a linear line here. This is the linear line, right? That will satisfy this value. Okay, so the convex, meaning the chord AB will lies above the curve. Okay, in 2D that is clearer. So convex is something like this. This one and this one is convex. Okay, and this one is non-convex. Why? Because when you put any line segment here, it will not go inside, okay, the shape. Yeah, it will pass outside here. Okay, so in linear programming, right? Usually the first thing that you learn is to create the boundary of the constraint, isn't it? Yeah. Graphical method, right? You start to draw the boundary, and then you check, okay, if the boundary is actually convex or not. Okay? If the boundary is non-convex, you cannot use linear programming, right? Okay. Up to here, any question? Okay. Good. So in terms of the optimization, again, the same thing. Unimodal and multimodal. Okay, I will explain about it this way. Okay. So here is the example of multimodal. That means you have several peaks. Okay. So point A here is a local maximum, right? Again, in this point is also local maximum. Again, this point B is also local maximum. In this graph, this is the global maximum, correct? Point D. Okay. What is the minimum? The global minimum is what? The global minimum is this one in the boundary, right? So this is local minimum, again this is local minimum, but you see here this is not continuous. Okay? So our problem here is whether the landscape is actually unimodal or multimodal, meaning that if you have many peak here, that is meaning multimodal. So algorithm like that use a gradient method. I think last semester you learned about Newton method, right? So if you use gradient method like Newton method, okay, it will always go to the local maximum or local minimum. Okay, so in that case, you need to be very careful with the initial condition. Okay, what is next here? So the function can be linear or non-linear. The variable can be discrete, continuous, and mixed. In this course, we will learn about integer programming also. Okay, I think next meeting. Now, what happens if you have many peaks in your landscape? Okay, in that case, probably you want to use population based or trajectory based. Okay, or they call this meta heuristic. Okay, so that you can get the global optimum. Okay. Now, in this course, our main software will be just Excel, or you can also use Google Spreadsheet with solver add-ons. Okay. If you like to use Python, you can use Python with SciPy. Okay. And I ask you to download MinSync, which is also a free software. Okay. The other software for optimization, many. Okay. These are just a few of them I put here. So I think this is quite famous software for optimization. Yeah? AMPL can have millions of decision variables, okay, which is usually used for a professional or OR. Okay, next. The next part is actually another type of optimization problem that I mentioned earlier. Okay, it's called CSP or constraint satisfaction problem. Okay, so you can check in Google. So if you Google it, you will find Wikipedia probably. Yeah. Oh, so there is a Wikipedia about CSP, content programming. Right. So, for example, using CSP, you can solve 8-queen problems, map coloring, Sudoku, crossword, and so on. So these are the examples. So in my slide, I give very simple example of grid arithmetic. Okay, so in this case, you have a set of variables and a set of domain with a set of constraints. Okay, so now the goal is not just to minimize or maximize, but to find the values of those variables that satisfy those constraints. So let's take example here. Okay, this is just a game, a puzzle. So say you have xy plus xy equal to zx. So x, y, and z are integer of one digit, yeah? From 2 to 9. So there is a domain. The domain is between 2, 3, 4, 5 integers, so until 9. Okay, and each having different values. The question is, what are the value of its letter here? X, Y, and Z. Okay, so please note that if X is 2, for example, and Y is 9, the meaning is not 2 multiplied by 9, okay, but it's a number 29, it's a digit. Right? So then the solution is something like this. So we know that y plus y equal x and x plus x equals z, isn't it? So that means 2x equals z, 2y equal x. That means what? That means x must be an even number. Similarly, z must be an even number, right? So because the digit is limited, the digits are limited from 2 to 9, so you can just try, okay? For example, what happens if I try y equal 2? Okay? So if y equal 2, x will become 4, right? And then z will become 8, right? So in that case, x equal 4, y equal 2, and z equal 8 is one of the solutions. So the solution is not necessarily unique. Okay, for your practice, okay, can you solve this? Okay, each letter is one digit integer from 0 up to 9, each having different value. Okay, so what are the value of each of the letter? So D is one digit, okay? Either 1, 0, 2, 3 until 9. Yes. So E is another digit. So either 1, 0, 2, 3 until 9. Okay. Now D plus E equal Y. And then you have a carry, right? So D plus E equal Y, there is a carry. The carry will go to N plus R equal E. Right? And then you have another carry, you put it in front, so that the second carry you will put into E plus O equal M, and then again you have another carry, that you put S plus M equal O, and then you have another carry that is equal to M. Do you think you can solve this? First thing first, do you understand the problem or not?
Yeah, each letter is a number,
Yes.
and the fact that it's next to each other means just next to each other. We don't multiply or do anything.
Plus, plus. There is no multiplication here.
Mm.
So there are many ways to solve this problem, okay? So one way is to create a permutation. Okay? For each letter, you permute 0 to 9. Wow, you will have a lot of combination, isn't it? Okay? So if you look at the website that I post there, okay, you will see I use a MATLAB program to permute. That means I will create all the permutation. Okay, and then I fill up and then check what is the actual permutation that produce these values. Okay, that is one way. Another way is use backtracking. So you try one by one. So you create a tree diagram. For example, T is equal 0, and then E is equal 0 also, or 1, right? Cannot become equal. So T equals 0, then E is 1, and then E is equal 2, E is equal 3, E equal 4. So you create a tree out of that, all the possibilities you try. So that is another way. Okay, but in here I give you very simple solution. So let's just do it this way. D plus E equal Y, right? But there is a carry, right? That carry mean multiply by 10, correct? Right? So then 10 equal to the first carry. So let's call this C1. The carry is C1. And then the second, what do you call that? You get C1 plus N plus R equal E, correct? Can you see the second digit from the right? So N plus R equal E, but there is a carry from the first one, that's first carry, and then it will produce another carry. So we call this second carry, so C2, which is actually 10 of that, right? And then go to the third one, to the third from the right, okay? So in this case, E plus O equal M. So E plus O plus the second carry equal N plus 10 to the third carry. Right. And then the same thing, yeah? So the third carry, you put it into the fourth column, right? So S plus M equal O, supposed to be, right? So, but you have the carry here. So S plus M plus C3, the third carry, equal O plus 10 of the fourth carry. And you know the fourth carry is equal to N. Must be, right? Okay, now you're having this equation. How do you solve this? If you have all these equations, how many? So 1, 2, 3, 4, 5. You have 5 equations and how many unknown? So you have 1, 2, 3, 4, 5, 6, 7, 8. Is that 8? 8 plus 4. So 12. 12 unknown. Right? Because we have 4 carry. So how do you solve this? You can solve this by putting everything in the left side. Okay, on the right side becomes 0. And then you can solve it using linear algebra. Right? You remember? Oh, something like this. Okay, so you create a matrix. Okay. And multiply by the factor, the one that you want to know. On the right side, you have all zeros. Right. Of course, with this, you can solve the solution. Yeah. Any question? So how do you solve this? In linear algebra, how do you solve ax equals 0? You cannot take the inverse because it's 0. How do you solve that? Do you remember? You took linear algebra, right, last time? Yes. So, did you learn about Gauss-Jordan? Using RREF. Huh? Reduce form, RREF, reduce echelon form.
Oh, that, yeah,
Yes.
we learned that.
Okay. Okay, so you use that to solve this kind of problem, okay? So you create the REF or RREF, then you can solve. Okay, so you can try to solve similar problem of CSP. Okay? So say base plus Paul equal games, okay? Or Gerald for Donald equal Robert, or attraction intention equal regeneration. So these are just puzzle. Eh? I remember you create Sudoku last semester, right? So the same. So you can also use CSP to solve Sudoku. Okay. Okay, up to here, is there any question? Devi, Joy? This is just a review from what you have done last semester. Okay, the last review is about linear programming. Right? So linear programming. Okay. You have learned this last semester and we just review it today. After this, we will go to the real material of this course, right? So, yeah, you're supposed to perform sensitivity analysis, but I will not put it here. Anyway, so if your constraint and objective function are both linear function, okay, then you have what is called linear programming problem. then you can solve using simplex method, right? So it was formulated in 1947, and they are actually using it during the World War II. Okay. Again, this is exactly the same as earlier. So I said this is the general LP problem. Okay, and if you look at this is a standard form, right? Why this is a standard form? Because it's only maximizing, yeah. Okay, only maximizing, and then the constraint is only equality. So this is a standard form. Okay, so for any optimization problem, okay, all you need to do is to check, okay, what is the objective, okay, what are the decision variables, right? What are the constraints, okay? And then you will find the relationship between the objective function and the decision variable, okay? And then once you get the decision values, decision variable value, you put it back into the function, the objective function, to get the optimal value. And then you perform what is called sensitivity analysis. What is sensitivity analysis? You change the input a little bit to the right, and to the left. Huh? So you want to have solution that is actually less sensitive. Okay. Now, the most important here is actually to formulate your optimization problem. So you need to decide the unknown or decision variables. Okay. And then you identify the constraint and identify the objective function. Once you have this, then you transform this mathematical language into the spreadsheet or into the solver. Then you just solve the optimization problem using computer. Okay. One of the problem that often used in industrial engineering is called transportation distribution problem. You learned this last semester, isn't it? Transportation problem, correct? Yes. Okay. So let's use the same example. Okay. So transportation distribution problem is very typical. Okay. You have a number of supplier and a certain number of outlet to represent the demand. Okay. And then the unit cost of the transport goods from each supplier to each outlet is also known. So now the problem is to find the number of goods shipment from each pair of supplier and outlet so that the total cost is minimized. Okay. Now, since you have known that, so can you solve this problem? First thing first, can you formulate this into the optimization formula? So suppose we have a computer company with two warehouse A and B, and there are only two retail shop, yeah, Y and Z. Okay, so warehouse A has 250 computers and warehouse B has 400 computers. The retail shop Y need 300 computers, while the retail shop Z needs 200 computers. So the table below represents the shipment cost, okay, from A to Y and Z, from B to Y and Z. So the question is, how many computers should the company transport to minimize the cost, to minimize the total cost? So this is a practice. Can you start to do it? So how many variables here? How many decision variables that you have? what is the objective function? What are the constraints? Can you make it? There are many ways, but you can propose. So if you look at the table, right, you want to minimize the cost. So what are you going to do? Any idea? Okay. How many warehouse?
2.
2. How many outlet?
2.
Okay. So then 2 times 2, you have 4.
Yeah.
Is there any 4 cost there? Right? And what do you want to know? What do you want to know? What do you want to know? How many computers will be transported from the warehouse to the outlet? Correct? That's what you want to know, right? So let's call this A. Oh, no. Let's call this X. Okay?
Right.
How many X that you have here? What is the name of the warehouse? Okay, A and B. So then you have X, A to Y. Yeah? Next you have X, A to Z, right? The next one, you have X from B to Y. And then X from B to Z. So you have 4 variables. What is X again?
The number of computer.
Yes, the number of computer, okay? So from a warehouse to the retail shop, right? So say I will name it XIJ. So I is the warehouse, J is the retail shop. So you have 4X in this case, right? And then the objective function is to minimize the cost. So how do you calculate the cost?
Multiply with the this
Yes,
one, the shipment cost.
correct. So 18 multiplied by XAZ or AY, right? And then plus 15 multiplied by XAZ plus 12 multiplied by XBY plus 14 multiplied by XBZ. Isn't it? Okay, that's the objective function. So how about the constraint? What are the constraints? Warehouse A have 250.
This one, retail.
Right? So warehouse A has 250. So
Oh.
that means X
A.
AZ AY plus X AZ equal to 250. Right? The same with warehouse B. How about retail shop need 300? What does it mean?
So equals so XAY plus 3Y
Okay, equal 300.
equal 300. Yeah.
Yes. Okay. So then you can start to identify the constraint. Okay, the total supply from the warehouse cannot exceed the capacity. So can be less, right? Okay. But the total demand must be satisfied. That means equal, right? So now you have the objective function, you have the constraint, correct? Of course, you have boundary conditions. That means all uh, the x, I, j must be positive or zero. Okay. So can you solve that? So first you write down the optimization formula. Okay. Minimize objective function subject to all those constraints. Huh? So once you make the formulation, inputting into computer is rather easy. Once you make it, show your result and your LP formulation also. Okay, done. Yeah. The most important part is to create this LP formulation, right? Something like this. Okay, so once you can create this, then you can use Excel or you can use Minisync, for example. Okay, so in Minisync, okay, all you need to do is just copy and paste this and then into a Minisync. Okay, so in Minisync you will create the variables with certain range. So for example, 0 to 1000. And let's name this XAY, XAZ, XBY, XBZ. Don't forget the semicolon here at the end. And then we define Z is the objective function as float. And then you set up all the constraints, including the objective function. Yeah? So this is the objective function, right? The Z equal 18 plus something, something. And then you solve to minimize the Z, and then what do you want to show? Yeah? So if you run this, so I will show, I will just copy and paste this one. Okay, and then I put it in Minisync, right? So I just copy and paste, and can you see it? Oh, I think there is a problem here, so I need to output this one. Okay. So if there is an error, the Minisync will start to show the error. Okay, and then we just run this. When you run, I think the basic of Minisync is geocode, but to run this, you need to use the CoinBC. This is the solver that we use for linear programming. Okay, so there, you got the result. Can you see it? So this is the result. Yeah, you get the A, X, Y, A, Z, and so. So you can also use the same thing in Excel. Okay. Similarly, you can also use, instead of integer, you can also use a floating point, right? So you can see exactly the same, except earlier we defined it as integer here. Now we define it as float. Okay. Again, you just copy and paste and run. Right? Any question? And the most important is to create the optimization formula. Okay, once you put into formula, you just translate into the solver. Okay, let's continue next meeting then. Little bit here. Do you want to put this as assignment or you have too much assignment already?
Okay, I'm trying out the software right now. Took me some time because I forgot how.
Okay, okay. Let's do it as assignment, okay? So that we can discuss it next meeting.
Okay.
Okay, exactly this one I just copy and paste in Lentera, and then you just submit it so that you have practice, right? Okay, so thank you for today.
Okay. Thank you, sir. See you
Bye
next
bye.
week.
See you next week.